welcome back to another day of science. So yes, let me just check my mic one moment. Yep, it works. So hi, I'm Millennium, Isekai'd Mask Knight Empress Scientist, and today we are going to discuss the model systems. But actually, before I start, I have to do 120 jumping jacks. Why? Because it is for a mini celebration, aka it's the 12,000 subscriber celebration going on for this channel, and I'm trying to do 1200, so 1200 of those, and we are on day 2 of the jumping jacks. So let me just do the second set now. One moment. All right, and the biggest proof would be the heart monitor. So yeah, I'm gonna wait, let me just stretch one moment. Okay, here, let me start counting. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, let me breathe 1 second. So 30, let me just write that out of like that. Okay, 30. Let's go. And 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Wow. Oh, let me just write 40 jumping jacks out of 120. Last time we did 120 plus blank. Today it should be 240, okay? Alright, continuing. 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60. Halfway there. Almost. Okay. 60. Just update this on 60. Okay. 61, 62, 63, 64, 65, 66, 67, 68, 69, 70. We'll get there. Slowly but surely. Wait, let's erase this part. 70. It's at 70. Okay. A little bit more. Okay, go. 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 90, 90. That's a lot. 90. Almost. Water, water. Water, water. Okay. 30 more. Okay, go. 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 110, 108, 109, 110. 110. Just erase this part. 110. Just 10 more. Whoa. Okay. 10 more to go. Let's go. Wait, what was it? 111, 112, 113, 114, 115, 116, 117, 118, 119, 120. Whoop, whoop. Okay. We reached 120. Where's my tubig? The tubig is here. Okay, but 100, 120 jumping jacks. Day 2, let's finish. Day 2 finished. Okay, and then we'll update this note. Yeah. 240 star. Okay, and our max this time is 153 heart rate. Beautiful. Much better because last time it was 163. You know what? Good progress. Good progress. Plus 2 years lifespan. Okay, now on to the lesson. Let's go. So model systems, okay? Model systems, what is it? What is a biological model? It is an experimental system, okay? And you use it to check the specific trait or phenomenon of the living organism that you're checking. And these things actually would be like a stand-in for what you're actually trying to study. So let's see, I'm gonna write it out here. Can I write it? Yup, I can. So yeah, model systems. Stand in for the trait. Stand in for the actual organism. Actual organism. So for example, could be a mannequin. That's your mini model that you could try, and you could try and dress it up first if you don't want to dress yourself up and stuff like that. So when do you need biological models? Wait 1 second, I'm getting a hair clip. Okay. When do you need a biological model? So it's when studying a trait in the human context is impractical or unethical. So you can actually use like stem cells if you want to study humans, for example, because maybe getting a human to dismantle and try on would be a bit difficult, you know. You would need some ethical processes for that. All right. And models are everything because the model that you choose, it will actually determine the experiments that you can perform and the quality of the results that you might get. So that's why you have to check if you're actually using the right model for it, because it would be really difficult if you chose the wrong one expecting some specific results. That's why you need to choose the right model. And how do you choose the right model? That's a very, very good question. So let me see. I'm gonna erase it. I'm gonna erase a thing. Erase. erase it. There you go. Okay, so how to choose a model. There are certain factors for that make you decide how to choose your models. Let's see. Yeah, there's a couple. The first, you want to reproduce your trait of interest. Okay? And one thing about that would be if your model organism doesn't show the trait that you want, then that might not be the greatest model thing to choose for your specific trait. Second is it will allow you to dissect the basis of that trait. So again, make sure that it actually matches what you what you need. And let's see. In practical terms, you would need the likeness, a very obvious likeness to the trait. So again, just making sure that the trait you want could be seen on it. So how do you know if the system that you choose is actually reproducing your trait? So you can't know with you can't know with certainty at the start of your investigation, because some models could mimic a trait but not actually represent it, and finding a model may not always be true or easy for your trait of interest. Okay. So what approaches are used for models? There are two approaches. You have genetics. Let's see. Okay, there. You have genetics and you have reconstitution. So again, let's erase this. Genetics. AKA, you would mutate the genes to uncover those responsible for the trait. And then reconstitution is rebuilding the trait from component parts. Again, so two important molecular interactions for it would be genetics and reconstitution, and both approaches would screen for the function and reveal the action and impact of the molecules. Types of models. Okay, that's a good one. For the types of models, you have the living organisms, you have the cell culture, cell-free, and mixed. These are systems, okay? So again, 4 would be, let's erase this, just to make sure that I reiterate it. You have living organisms, you have cell culture system, you have cell-free system. Howdy, what's up, George? Welcome back to the stream. And we just finished 120 jumping jacks again, so we are at 240 out of the 1200 that we aim for the 12k celebration. Whoop whoop. And you're actually just on time because we're discussing the types of biological models, aka living organisms, cell culture, cell-free, and what's the fourth one? The mixed systems. And the Pal World update is literally in, I think, less than 24 hours. Maybe. We don't exactly know what time zone they were referring to June 25. But we have to watch out for that one. Yes, so that's a mini thing that might happen if it gets released on time or at an hour where I can stream. Yeah, but yeah, that's the living organisms as models. For living organism, I mean, that's the types of models. For living organisms, that would be animals, plants, and microorganisms. And then you also have the cell culture one, aka outside the organism. Cell-free would be just the pure molecular components without the intact cells. And then you have the mixed system, aka the cultured cells that are transplanted into the living organisms. Okay, so start with the first one. What's the first one? The living organisms. Erase, erase, erase. You have the living organisms. Okay, so for living organisms, that could be, there's a lot of this one. Could have prokaryotes, could have fungi, plants, invertebrates, fish. Saba is coming. They will start streaming. Was it June 28th or 26th? But yeah, woof. So we have prokaryotes, fungi, plants, invertebrates, fish, amphibian, rodents, monkeys, and the viruses. Those are examples. So for let's see, advantages, what area would you say all of this falls under? Good question. I think this would be more biology because the notes I'm reviewing are from the molecular and cellular biology section. So that's a thingy that I need to focus on for the next about 2 to 3 weeks. And then hopefully we can breathe a little bit more, hopefully. But that's why I really just need to put this in my head properly. So that's why we have these. For why we want to use humans, no, not humans, living organisms, the plus would be they best represent the natural context of traits, natural context, and they allow the demo of the traits biological basis and can show the very complex interactions because it's just a very natural setting. However, the why not, why it's hard to use these, it would be normal, the tractable model organisms could be simpler, but they diverge significantly from human systems. And organisms most similar to human might be expensive and slow. So for example, using primates, like the first thing you think about for primates would be when gorillas or something like that. That would be hard because it's a bit hard to take care of. It's a bit huge, and the complexity, a positive trait could also be negative because it's hard to pinpoint molecular causes of the observed traits. And 4, so that's the big monkey. Yes, just like what Vox and Calyx likes, big monkey. Or Sea Dog. Yeah, that's why. Okay, so we discussed living organisms. Let's go for cell culture systems. Cell culture. Cell culture. There you go. So instead of studying the whole organism, you can actually isolate just the cells, right? So you have 2D and 3D cells. Oh, I just remembered. This avatar right now is 2D, and hopefully in this lifetime we could get 3D. I don't know how. But yeah. Well, more music videos then. So yeah, for 2D cell cultures, the cells would grow. There are different types. Ooh. This could be I'll lessen the thickness of this one. Oh yeah, I think there's I think you saw it. One of the, I'm not sure about the Chibi 3D model. It may be the, okay, so I would really like to do the sword. This is me. This is me with the hair and the swords. Yeah. So we need to keep the swords and be able to use this one to do like ice cream, and maybe Beat Saber, and then do the project of Beat Saber, and then do the project Aincrad Sword Art Online. Those are the mini tidbits that, yeah. But right now, maybe just go into more MVs. Yeah. So that's what right now I'm focusing, but it would be really, really awesome. I don't know how one day to be able to dive into Sword Art Online and live through it. Please, we need to live through it. For the 2D, there are different types. So the types would be adherent cultures, aka the cells would attach to the flat surface. And then you have suspensions, they float. Immortalized cell cultures, where the cells can divide indefinitely, like the HeLa cells, and the primary cells, where they have a very limited lifespan. Okay, so advantages of it would be, it's very simple. Oh, that's right, plus and minus. It's very simple, easy to manipulate, and very ideal for processes like gene expression and stuff like that. But because it's very isolated, it's not as natural, like it's not in the environment it should be in. And cells may change their phenotype over time because you took them away from their natural home and they're going far away. Meanwhile, if it's the 3D cell culture, ooh, the cells, oh my gosh, wait, speaking of 3D, not the 3D model, but I just remembered, there is a chance that another karaoke stream, because first of all, we have the light stick emote now, and I'm just trying to gather which like songs. So I'm trying to see which anime songs, which maybe K-pop songs and all that. I'm trying to gather a list. Whoop whoop, yes. So that is where it's at. But aside from that, there's this ACAD thing that I gotta finish. So that's why we have these science streams. Hello, Unknown. What's up? We are discussing model systems and like a possible schedule of a karaoke stream, gathering some anime song ideas, of course. Oh, and I think in the next karaoke stream, I'm not sure if it will be archived. Most likely it will be unarchived depending on copyright and stuff like that. But I'm working towards it having music, at least, because last time we had an acapella before. And this time we have to do like a version with music. My brain can't digest so many words at once. It's fine. It will have to digest it at some point. It is what it is. But yeah, so for the 3D, the cells, this you have the type. You have a couple of types for these. You have the scaffold and cell organization. Because if it's the scaffold, the cells would grow on a matrix mimicking the extracellular conditions. But if it's self-organizing, then they would form spheroids or organoids. The plus of this, it's very, very close to real tissues and can recreate your oxygen, nutrients, and waste products in actual organs. But the big negative of it, what do you mean? I am discussing science, aka model system, and we are at the 3D part of cell culture, where you have scaffold or cell based, but positive, the pros of it is it's very close to real life, but the big con of it, it's very complex and hard to take care of. Yeah, right. But the big question is, what are organoids? That's a good one. What are organoids? Erase. organoids. So they are 3D. Where can these systems be found? It's more like you choose them depending on your lab. Um, Not lab. For homework? No, it's not necessarily homework. It's a life thing where science is embedded into your life because introductions. So I'm Millennium, Isekai'd Mask Knight Empress scientist. So sometimes I do science, sometimes I do Pal World, sometimes Pokemon, or randomly rage over Netflix and not Netflix. Hello, Rayborn. Millennium Sana, can you teach me the three different zones? One moment. I'm still starting the organoid section, but I don't know if I'll go that deep into the zones of it. But yeah, so they are 3D structures grown from stem cells, right? And they can like self-organize into miniature and simple versions of real organs. So normally, okay, let's talk about, I'll bring up stem cells again because in an isekai environment, it may be something that I work with. I can't copy the text to translate it. Yeah, no problem. It'll work out. When life throws you lemons, make a lemonade. It is what it is. So for stem cells, you could think, oh, it's wonderful. You could use it as a model if you have like a human that you would like to like do an experiment on, right? Okay, no, I termed that really weirdly. No, it's more of, let's say you have a patient, a cancer patient, and you want to try out different drugs on it. But you can't just willy nilly give medicine to a patient that's not yet tested. So we are at the testing range. So you could say, oh, okay, I'm going to try it on their stem cells, but there's the embryonic stem cell, or a different type of stem cells, the induced pluripotent stem cells. So you might think, oh, okay, embryonic stem cells, the one we naturally think of. It might be a bit more, for a lack of a better word, controversial, because the way you would like get some would be if you have a blastocyst and then you have the inner cell mass, and then you take some from that one, and then and then outside it would then just proliferate and all that. But then, so it's this angle that might be questionable. So that's why we use the induced pluripotent stem cell route. That would be if you just take, let's say, you could get it from like a blood cell of a patient, like a blood sample. Am I selling courses? No, it's just here in the bods as bods. I just leave them up here. Just for example, if you have a salad bowl, they're in the salad. They're just here. Yep. So for example, you have blood cells or skin cells. Yeah, these are just there for free, and then you could reprogram them by putting the Yamanaka factors if you are in a specific lab that works with them. Yes, the salad. Oh, there's a salad emote. That's good to know. Yeah, you could have the Yamanaka factors, specific magic syrup stuff, where you tell them go back to your stem cell original phase, and then you could tell them to become something else. So it's okay, but I need more space. We don't have enough space. We have, so all cells come from like this one, right? Stem cells, and that blood cell came from a stem cell. So right now we're trying to get the blood cell or skin and make it go back to stem cell, and then we'll tell it to become, let's say, a cardiomyocyte, aka a heart cell. And now you have a heart cell where you can test out different medicine that you want, and you want to see what happens to the heart, quote unquote, of a patient. Ta-da! See, now it's like in Sword Art Online, if what was it in the super in Alicization, I think it was like the fluctuates and all that. I'm not sure if that's the right word for it, where they had like a copy of the different humans, and then they, like Yujiro and Alice and Kirito, grew up in the virtual, is that right, the virtual world and all that jazz. So they have a virtual copy of themselves there, and in the human world they're also growing. Yeah, you have to understand what's written here. You have to look at it with your heart. This is a test. It's like the emperor's new clothes or the emperor's new whiteboard. You have to look at it and understand it with your heart. It's not necessarily with your eyes. So you just have to feel. You will see the words if you believe in the heart of the words. Yes, believe in the heart of the cards as well. So that's stem cells. So for organoids, they are grown from stem cells that can like reorganize into the simplified versions of real organs. So they replicate many features of the tissue of origin, like the different cell types and all that jazz. They start from pluripotent stem cells or adult stem cells, and then you culture the cells under very defined conditions, which mimic developmental signals that the tissue would experience. So why do we want to use organoids? Okay, let's nope, erase it. We want to use organoids because okay, it would preserve the complexity of like the cellular complexity of how it's built and the 3D structure of the tissues compared to yes, good, compared to the traditional 2D culture. And they can like autonomously form structures such as crypts and layers and all that. You could also use CRISPR if you want to modify it. And it's more in terms of uh, drug screening. It's more predictive compared to 2D cultures because they replicate the natural drug penetration and metabolism and different responses. However, the organoids, let's see, it's quite incomplete. Yes, CRISPR, clustered, regularly interspaced short palindromic repeats. Oh wait, sidetrack. I want to try explaining CRISPR again. So for CRISPR, you have clustered, regularly interspaced, short palindromic repeats. So you have something. What do these words mean? So you have. Let's focus on the word palindrome first. You have race car. If you read race car from backwards, race car, it's still the same. So that's a palindrome. And short palindromic repeats, aka race car, so they're short. And they repeat. Interspaced, appropriately spaced, and they're also clustered and regularly interspaced. So just think that's CRISPR. And now we want to check what like the process of it. So in like you have, and let's say you have a note and there's something wrong here and you want to edit it in like in humans, you could use the CRISPR-Cas9 system, not just humans, like living things and all that. You could use the CRISPR-Cas9 system where you have the Cas9 nuclease, Cas9 protein, and you have the guide RNA here, right? The Cas9 would cut it would cut the DNA strand. And then this guide thing would go to the specific, no, not RNA, but essentially a single guided. This is SG. This would be the guide, or DNA or RNA, one of the guides. It would tell you where the thing to edit is. So for example, you have a chromosome, you stretch it out, and then you now have, you reveal the specific gene, the specific area now. And let's say this part is wrong. The TTAGC is wrong. And what would happen is, nope, I'll erase this. I'll write it again. You have TTAGC. What would happen is your guide would go here because it found it. The guide is big. Some companies will make it T, so it's AATCG. Just flip it. A is partner with T, G partner with C. So it found it, and then your Cas9 would then cut. It would cut it here. I'll draw it again. So let's say you have a very long strand. Your TTAGC is here. So your guide RNA DNA would go here. It found it. Your Cas9 found it, so it will cut here. Bam. And so let's say it cut here. Now your dear scientists could then put a different thing here or something, or the DNA repair mechanisms would try to fix it, but essentially it won't be, like, naturally sometimes it won't be able to fix it perfectly. So that's how you induce knockouts that you want. Knockout would be if you knock out a certain gene. What does that mean? It's good. This one's good. This is a good flow. 1 second. If people say, "Oh, I knocked out the gene," KO gene. What? Oh, I'm gonna explain this part. So remember how DNA, mRNA, protein, that's the central dogma. So if you knock out the gene, then you won't be able to get your protein. So for example, I want an example. I can't think of an example right now. Let's say, yeah, essentially that one. Just if you knock out the gene here, then you can't transcribe it into the mRNA, and you can't if you don't have the mRNA, you can't translate it into the protein. Boom. So that's how it works. Okay. Now going back to the pros and cons of organoids. That's a very, very good suggestion that I'm not sure what it means, sadly. So, but yeah, don't worry. We can just continue writing it this way. So you have what's this called? The pros and cons of organoids. So pros would be, okay, it's complex, but it's a good version of complex because you can try out more stuff on it. However, the negative part is many organoids would resemble the fetal or immature stages of the tissue and not exactly its fully adult form. So, and they don't exactly have blood vessels. So it's not, yeah, it's missing a lot of things. It's missing immune cells, nerves, and mechanical forces are often absent unless you really engineer it in. So that's why. But yeah, those are the pros and cons of organoids. Now for the cell-free systems. Good. Very good. What's this? Very good. Next part. Let's erase this. Erase, I said. Erase it. Okay. Here you go. You have the cell-free system. So these are mixtures of molecules or machinery extracted from living cells. So they're used to model the traits that depend on molecular and subcellular processes like your transcription, translation, DNA, and stuff like that. And it's composed of very purified molecules. So, what is that? Oh, a shape. Very purified molecules. We can use shapes here. One moment. Oh my goodness. What Okay. I should really explore actually. This is amazing. A shuriken. Okay. Don't get distracted. Calm down. Focus. 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 Advantages of the cell free is you can dissect the very specific molecular interactions of a pathway and stuff like that, but it's but you still removed them from their natural environment, so that's not really good. And it's not good because the things that should happen in a normal condition might not occur properly, and molecules might act differently than they would inside the living cells. Oh, I'm not sure where everyone is, but if you are experiencing the heat wave at a certain part of the world, drink water, please. Because sometimes, in some areas right now, it's reaching 100 Fahrenheit or close to 40 degrees Celsius. So the too big or water is important. All right, so mixed systems, they combine cell cultures with living organisms. So mixed systems. First, you isolate and expand or modify cells in the culture. Two is you put it back into the living organism like an immunodeficient mice. So this approach is very important because they test whether cells would form the specific tissues or generate the tumors if you put them back. However, the cells can change while growing in culture, so they might acquire abnormal properties that could affect their behavior if they're transplanted back. Okay? Now, the use of genetics in model systems. There are two major approaches to using genetics in model systems. You have forward and reverse. I have to write that. Forward and reverse. Same as in a car. Forward and reverse. Forward genetics. Forward genetics. And reverse. So forward is you identify a phenotype. You identify a phenotype and then find the mutated gene responsible. Gene. Reverse genetics is when you start with the mutated gene and study the phenotype. Wait, you know what? Let me write that in a different way. You start with a mutated gene and then you study the phenotype. So again, I will close my eyes. Forward genetics is when you start with the phenotype and then you try to find out find things about the mutated genes for it, and then you have the reverse. You have the reverse one where you start with the mutated genes and then you go and check what's up with its phenotypes. So for forward genetics, you can perform experiments with living organisms or cultured cells. So you first want to obtain a population with a gazillion of the random mutations. So random mutagenesis. They cause unexpected mutations across the genome and could provide unbiased screens. So after you generate the mutants, the second step is to screen the mutants, and you need the organism with fast breathing, small size, and simple stuff like mice, fruit flies, and zebrafish. Once the mutants are isolated, then you identify the gene. Advantages for it would be it would reveal which genes are causing the trait. However, it's more of you get what you screen for. So if the screen is not designed carefully, then you might miss some important genes or find irrelevant ones. And that's why the success of forward genetics heavily depends on how well you define and select for the phenotype of interest. Do not mind the 110 heart rate. It's just stress. Okay? It's just stress. Next, reverse genetics. Now you flip. Hello, Sheriff. Greetings. Hat tap. We are discussing genetics right now. The forward and reverse genetics. Forward being you start with your phenotypes, like a gazillion stuff, and then you screen, and then you identify the mutated gene. And then you have the reverse genetics, where you flip it. You start with the known gene and you observe what happens. Oh, side note, we've done 120 jumping jacks today, so that brings us to a grand total of 240, including day one. So that's 240 out of the 1200 for the 12,000 subscriber celebration that we're doing, and cooking a karaoke stream at some point, maybe next month. Whoop whoop. That's why. Oh, also waiting massively for the next Palworld, the summer update for Palworld. Yay! Oh, and there a couple more science streams as well, because there is a thing that we have to finish and focus for. So that's what's up. Reverse genetics, you flip it, start with the mutated gene, and then you find out what happens and observe what happens when you have it. So it can be done on living organism and cultured cells, and it's powerful for studying gene function by creating either the loss of function or gain of function mutations. Now, you have two versions of reverse genetics. You have, oh my goodness, I have to sticky note this, pero naubos na ang sticky note. My gosh. Okay, it's okay. It's alright. We can find it. We can find more sticky notes. We have transgenesis and targeted mutagenesis. Erase. Reverse. So again, we have reverse genetics. For this one, two types: transgenesis, and what was it? Targeted mutagenesis. Transgenesis, what is it? Transgenesis would be you add foreign DNA constructs into living organisms, okay? Into living organisms or cells, so that you get the gene product that you want. So you have the gain of function and loss of function. The gain of function would be you increase the gene activity, but loss of function would reduce or inhibit the gene activity. So that's what it is. Now, what is targeted mutagenesis? So you precisely disturb specific genes. So again, transgenesis would be you add foreign DNA to get either a gain of function or loss of function, but targeted mutagenesis would be you target a thing and you mutate it, or it's just perturb specific genes. And there are a couple of types of mutations or variants. You have germline and conditional. Germline would just affect all cells by editing the early environment. And then you have conditional, where you just affect certain tissues or the certain types. And then you have the homologous recombination, still reverse genetics, where you replace an endogenous gene with a modified DNA segment. So it's very efficient in bacteria, but it's less efficient in mammalian cells. Alright. Then you have reverse genetics again for CRISPR, There's a couple of things. And you have RNAi. RNAi would use short RNA molecules that would guide the nuclease to target and degrade the complementary mRNA. So you get a knockdown of the gene expression. So models are everything. Hello, Dorkabo. Hi, another sensei. Salute. Oh 07. And we were talking about models actually. Not the stage models, but more of models, model organisms. So here's the thing, not all biological traits have existing models. So it's if no good models exist for your trait, it can severely limit your ability to dissect the mechanisms. Okay? And so what if I am teaching molecular and cell biology for this one, and specifically model organisms. So yeah, what if your trait has no good model? Oh, forgot to introduce myself. Hi, I'm Millennium, Isekai'd Mask Knight Empress Scientist, and we do Palworld, Pokemon, science, jumping jacks, treadmills, and all that here and there. So yeah, that's the adventure. And Palworld, did I say Palworld? I think I said Palworld. Oh, yeah, and the discussion of what's the best ice cream flavor, and that does not include choco mint. Please exclude that from the choices. In terms of languages, feel free to speak in English and Filipino. Yes, thank you very much. What if your trait has no model? Well, if there isn't, if you can't recreate it in simple models, then just think creatively about how to approach these traits. So when models fail, you use omics approaches to allow the large scale analysis of it. But, a major problem would be the molecules could interact with the others, so it's hard to see which interactions are interacting. Yeah. So RNA-seq, what is it? RNA-seq would identify and quantify the gene expression changes, and when one gene changes, it can trigger expression shifts in many others. It's like a train. Oh no, I was gonna say if one car breaks down, the others break down, but we don't want that. Remind me if there's a different analogy for this. But yeah, if one gene changes, the others could change as well. But not all changes are equally important. Some could drive the phenotype, some are just noise. So how do you check which interactions really matter? Well, an example would be the nude mouse, which lacks the hair and the thymus due to the FOX1 mutation, FOXN1 mutation. So this is a transcription factor crucial for epithelial cell function. So mice that have this thing wonky will have defects in their skin, mammary glands, nails, and pigmentation, and hair, and stuff like that. So again, what is FOXN1 for? If it's gone in a mouse, it has whacked up or non-existent, it's bald. It's essentially bald. Its nails are whacked, and it has wacky mammary glands. Okay? So it also has T-cell immunodeficiency and alopecia and abnormal nails. So how? So finding the nude-like loci. So the nude phenotype has been linked to the loss of FOXN1. However, it's really suspected that other genes work with it to control the epithelial development. So discovering these cooperating loci would help us understand the whole biological pathway for it, right? So from mice to flies, what's up? From this mouse, from this really, that's a mouse. From this mouse, beautiful. Half mouse, half chicken. Loci, thank you, Rayborn. Yes, loci. So yeah, if you have this mouse, that is a mouse. Please look at it with a very open heart and mind that this is a mouse. It's not a cat, it's not a chicken, it's a mouse. You have this mouse, and then you have You have a fly. Wow. I don't know if that's a dragonfly or a butterfly, but you have a mouse and a fly. You check the Drosophila limitations. So Drosophila melanogaster. It's a very powerful genetic model, but flies do not have hair, thymus, and adaptive immune systems. So take note, those three are things that the Fox N1 is related to. So modeling traits like those caused by Fox N1 mutations, it's not very straightforward because there is no definite likeness to it. So how what can we do? It's a good question. I don't know too. Okay, but the notes know. So yeah, you have fly, slack, and obvious likeness we want to model. So that's why we want to find a different model. So one strategy is if we put Fox N1 into flies and disrupt their morphology, right? So again, take note. If you put that in there, you disrupt the morphology and you could rescue or modify the abnormalities. Yes, the notes know, and by grinding the notes into our head, the head will know. And if it depends for the, which psychology or philosophy lessons, is the head equal to the human? We don't know. It might, like, if we discuss Attack on Titan, Eren is the Titan. We don't know. And if you watched Code Geass, it might also be a different angle. There's also Transformers. The controller is the thing, maybe. So again, you introduce Fox N1 into flies and disrupt the morphology, rescue and modify it, and you could also weaken the other genes. So it's modeling by disruption. It's like Blue Lock. Wait. What was Sias? Was it Quiet Disruption? Destruction? Beautiful Destruction? It's Sai versus Rin. They have different types of destruction. I think Rin after in the around roughly the end of season 2, Rin evolved into just pure chaotic destruction. That was a really, really good scene where, this might be spoiler, I won't say it, but watch Blue Lock. Get through the transcription, get through the PDF or PowerPoint version of the movements for a few episodes and you're good to go. It's good. The voice actors are also really great. Take note that Gojo Nakamura Yuichiro, the one who voices Gojo, is the one who voiced Shido, and Shido is a character that is really a great partner for Sai. And take note, Sai is voiced by Geto's VA. So the ones who chose the voice actors knew what they were doing when they hired these people. And Baro is voiced by Sukuna's VA. And then Nagi is voiced by the same one who did Mahito. So see, the people who hire these people know what they're doing. The fans who have trained ears will spot these interactions and will make memes. The memes will make the show more famous. And plus the plot is just really nice. No spoilers, please. Okay, modeling by disruption. So if you disrupt the interactions, those that amplify the small changes and lead to the large phenotypic changes will likely reflect the strong adaptive processes selected for evolution, aka if you screw up the small stuff and if the big stuff is screwed, therefore you attack the right one. Okay? Maybe, in these things, you never know, so you just have to keep trying. So strong disruption equals important function. That's what it says on this page. So, yup, good. Again, interactions harmful to flies might represent beneficial, powerful biological processes in mammals. Okay? So, so for example, rough eyes. Expressing fox and one under control of the promoter in the eye causes the rough eye. That means if you that means the fox N1 disrupts normal development if you overexpress it in the Drosophila. So, and if fox N1 is driven by the eyeless promoter, the flies develop small eyes. Therefore, okay, it's really related to the eye. And when fox N1 is driven by a heat shock promoter, the flies develop white bristles instead of normal pigmentation. It's really screwed, okay? It's really like, whoa. So, a genetic screen performed using 200 fly strains, each carrying different defined deletions, was done. And the suppression of the fox N1 rough eye phenotype was the primary readout or finding. So if a deletion reduced the effects, it was then tested against other phenotypes to identify the specific suppressors for it, okay? And 4 suppressors were found. Yay! More things! And one of the suppressors mapped is called Lilliputian. Or what you call Lily. The spelling is weird. Lilliputian. Putian. This one. Let's just call it Lily. And it would encode the transcription factor that would regulate the transcriptional elongation. Essentially, if it's screwed, then transcription is screwed, then translation is screwed, and therefore no protein, no phenotype, blah blah blah. That one. So that's why weak mutations in Lily reduce the severity of fox N1 driven rough eye and small eye phenotypes, which suggests that yes, good. That's the correct spelling. It's weird, but that's the gene called Lily. Spelling, I don't know why it's double L, but yeah. The weak Lily, the fox N1 and Lily works together, and they overall just cause developmental disruption. Just like in My Hero Academia, they're trying to prevent Shigaraki and All for One from meeting up, or else the world will explode. Ta-da! That's what's currently happening. So weak Lily mutations suppress bristle phenotype. And what else? So the conclusion is they synergize, and fox N1 also works with AFF4 for hair and skin. Note, if AFF4 is what's ablated specifically from the epidermis and hair follicles, does it cause the nude mouse-like phenotype? Well, if you knock it out, we'll see the results. And yeah, we can knock it out and you see hair loss. So it's out, so that's what it means. Like if you knock out a gene and you see hair loss, like, oh, that might be involved in it. And after a while, these scientists found out that AFF4 is essential for normal hair follicle development. And weak hair shafts happen as well if you have AFF4 or fox N1 loss. But why do the AFF4 and fox N1 mutants lack hair? You know what? I think some bald people also ask that. But in this case, the answer for why the AFF4 and fox N1 mutants lack hair, it's because the hair canal is clogged with broken hair fragments. So let's try to draw that. Draw it. Let's draw it. A beautiful drawing. So you have the hair. So you have the wild type hair follicle. Canal. And this hair, it will just grow, right? But in here, in the screwed up one, the growing hair, before it actually goes up, it breaks up here. After it breaks up, even if a new one tries to grow, it's clogged, so it'll keep on breaking up here, so nothing can go out. Nope. That's how The new and AFF4 knockout would produce hair that's bent or coiled because it's broken there and can't grow. Epidermal thickening. So, what happens when AFF4 is deleted from the thymus? Oh, we saw that already. Summary. Essentially, key biological interactions that are under positive selection would exhibit synergy and effectivity. Okay? So, there are some stuff that you need, some stuff you don't need, but some of them work together to help you. And by exploiting these properties, the researchers can uncover the selected for interactions, even when traditional forward or reverse genetics can't apply it. So that's why you have flash forward genetics, aka you evolve like, so what is it? It's for traits that evolve uniquely in vertebrates, evolving along a completely different evolutionary path to reveal important biological insights. Just remember flash forward. And so that's why screening or selecting for like the important things can identify the essential building blocks of traits when standard genetics might fail. And how can you find the important interactions? Well, just keep screening. You'll find it. You'll find it soon. And what defines a good biological model system? Okay, the mini review for the things we discussed today. What defines a good model system? If your traits can be seen on it, it reproduces the traits of interest. Why is the choice of model system critical in environmental biology? Good question. It's because of the different experiments possible, stuff available in your lab, in your city, in your country, how expensive those are, because and a poor model may lead to misleading results as well. And compare and contrast the forward and reverse genetics. Forward would be you have your phenotypes and you try to check out which genes are wrong with it, and then your reverse would be you start with your gene and then you check what's wrong with what genotypes are found. How do 2D and 3D cell culture systems differ in terms of relevance? 2D, very simple, but not as complex, obviously, because it's simple, but it won't be able to show your it's not the natural environment. 3D cultures, including organoids, would better mimic the in vivo environments, but it's harder to maintain. What is the fourth dimension? Good question. Welcome to the stream, Sangle. I am not sure. All right now, the word dimension would trigger Breaking Dimensions from Hololive EN. So the song literally played in my head when I read that. It's playing right now in my head. Stop. It has to stop. But that's the newest song. That's not really a new song, but that's the current song that's echoing. Yeah. And like that's echoing in my brain right now, and I would really like to, I would love to make a full cover for it. It's just gonna take some time. It's gonna take time. It's really gonna take time. But slowly but surely, we have to simmer. The adobo will not immediately be finished. You have to simmer it so that it's very soft and delicious. So why are organoids considered an intermediate between the cell cultures and living organisms? They recreate the tissue architecture. What are the strengths and limitations of cell-free systems? No. You allow the precise control, but it's still not very exactly a representative of what you might want to see. But if you want to see just the manipulation of it, then fine, feel free to use it. How would we test if a new gene identified in the flies also play a role in mammals? Well, we can check the homologs expressed in relevant tissues and generate the knockouts in mice and check the phenotypes. How would we distinguish whether FOXN1 disrupts fly eye development through transcriptional misregulation or structural protein interference? Good question. What was the question? How would we distinguish whether FOXN1 disrupts fly eye development through transcriptional? What is this? Wait. How can we distinguish whether FOXN1 disrupts fly eye development through transcriptional misregulation or structural protein interference? Okay. If it's transcriptional misregulation, you can do RNA-seq, because RNA-seq would it would show you the mRNA and things like that on, and but use controls, and you could stain for epithelial markers to check the disruption so that you can see the protein interference happening. Compare the patterns to how would you use rescue experiments to prove that lilipution is the gene responsible for FOXN1. Oh, you reintroduce the wild type Lily into a Lily mutant suppressor fly and check if your FOXN1 phenotype, the rough eye and small eye, is restored, and successful restoration proves the causality that you want to see. Okay? And I think for model systems, that's it actually. Yeah. How much radiation is harmful? A lot. Well, not just a lot. Normally try to not be exposed to too much radiation, essentially, because anything too much is bad. Too much burgers, too much French fries, although they're delicious, try to not eat a ton. But yes, for model systems, that is all for today. Thank you for learning more science, and we will be back at some point for more either science or Pal World. Adios. Where is it? There you go.